Hi. So I've had some requests to go through my Verifiable Transformers project. So that's what I'm going to do in this presentation. And I've kind of put a pause in this direction because there's just tremendous surrounding research work that has to be done if this direction were to actually work at scale. But I'll go through it, and if you're interested in collaborating on this, please let me know, and I can always reallocate my attention. So let's get into it. And the idea is that I'll cover the motivation, the theory, the surrounding research that needs to be done. I'll cover some of the challenges and how I solve them. We'll dive into the code a little bit, and I'll talk about future directions. So that's the structure of this presentation. And just to start, I want to talk about how we select techniques and interpretability right now. And a lot of the time, it's based on what techniques are actually relevant on the timeframes that matter. So safety is an issue right now and in the foreseeable future. So as a result, people use things like linear probes or SAEs. They use chain of thought monitorability. They use things that can be deployed right now. But what I was wondering is that there are areas in computer science where you can get much stronger guarantees, and that's formal methods. Like, for example, in type systems, you can have strong guarantees about the type of a particular object. With formal verification, you can guarantee that an integer will definitely not overflow. With an SMT solver, you can prove that two programs are equivalent on some specified domain. So these are the types of guarantees you can get in formal methods. And my question is, how close can we get to that in interpretability for transformer models? So the first question is, what kinds of guarantees would we even want? And I don't formally specify all of these properties. I'm just giving some high-level motivations. So maybe you're doing some medical use case or financial use case, and you want to make sure that your transformer model has the correct answer for all of the inputs that you care about. So I specify this in sort of a contrived way, and I just say, let's assume that there's some program P that maps inputs to the correct answer. Then if your transformer F matches the behavior of P on all of the relevant inputs, then we say that that transformer is correct. So that's a formalism for this, but there's other properties like robustness. So the weights within the transformer are continuously perturbed in some sense, because with every training iteration, we move the weights around a little bit. And you don't want the task decision to change. If you're doing like a really mission critical task and you're using a transformer, you don't want it to be oscillating rapidly based on just single training iterations. So that's what this robustness property is getting at. There's this concept of invariance. So maybe you're doing math and your model can't distinguish between polynomials of degree n versus n plus 1. Internally, those look the same to the model. And that's kind of a contrived example that's very unlikely to be true. But my point is that I'm just collapsing all impossibility results within this property. And my question is, how close can we get to these kinds of guarantees on non-toy examples? So real models and real properties that people care about. And this is what a normal transformer model might look like. So I'm just using GPT-2 as an example. It's a pre-norm, so you have some layer norm at the beginning, takes an embedding, you have softmax attention, you have a GALU activation, might have another norm somewhere in here, but these are the major operators that you're going to be working with. It repeats some number of times, and you end up with 100 million parameters. So actually encoding 100 million parameters is very difficult in an SMT solver. So the question is there a more efficient way that we can reason about this? And that's where circuits come in. Where circuits are subgraphs where if you ablate the remaining neurons, so if you replace them with 0 or with their mean, then that subgraph explains, or it's equivalent to the model's behavior for some specific domain. So that's what a circuit is. And we're just going to assume that there's a circuit that actually matches the model's behavior. So it's high fidelity, it's stable, so it doesn't change around. It's not like the circuit is some neurons one day and then it's some other set of neurons another. And it uniquely explains the behavior. So these are strong assumptions, and I'll talk about that in a second and how we might get around that. But my point is that we're going to be making claims about these circuits. And if you're making claims about circuits, that doesn't necessarily translate to claims about the model as a whole. So that's what I'm getting at in this claim discipline paragraph, where I'm saying we're operating on a bounded domain, we're looking at just the circuit behavior, it's a restricted vocabulary, and so forth. So even if we're able to prove claims about circuits, what would it take to actually make this usable to prove meaningful safety and interpretability properties in a real model? And that's where all this stuff comes in. So maybe there's multiple circuits. So I give a formal specification for redundancy here. And presumably you'd want some efficient procedure for identifying when these redundancy properties actually hold. You might want to prove causality. So maybe you have a circuit and it fully matches the model's behavior, but it's not actually causally responsible for that behavior. So that's where proving causality comes into play. This is a standard definition of faithfulness. Selecting the domain matters a lot because you might have proven your properties for some subset of the domain, but then there's some other input that violates the rules that you really wanted to hold true. So how do you select that domain efficiently? In some cases, there's like a natural bounded domain you can use. In other cases, it might be more complicated. How do you use this in practice and so forth? How do you make it tractable for the solver? So what I'm focusing on in this project is really this last bucket. And specifically, I'm trying to find SMT-friendly versions of those operators, layer norm, attention, the activation, such that we're able to prove SMT properties about the model. So this is what the guarantees actually look like that I'm able to prove. So this is functional equivalence, kind of similar to the definition given previously, but it's saying for all the elements in the domain, does the task decision, so that's a D sub T, for the circuit with edges E on that specific input, match a particular program? And if that's true, then we say that this circuit match is equivalent to the program on the relevant domain. So that's functional equivalence. Edge necessity is saying that for every edge, there exists at least one input where removing that edge causes the task decision to change. It's an invariance, so it's that same property I mentioned earlier. So this is like an invariance relationship. If it's true, then the task decision is equivalent. And this robustness property is worth diving into because one, it's kind of cool because it's a continuous property. So it's a proof about a continuous space, which is otherwise very difficult to achieve. Because if you're sampling manually, you'll never have a continuous guarantee. So that's the reason why I like this property. The downside is that it's not nearly as strong as what I talked about before. Before I mentioned weight parameter robustness, where you can jiggle the weights around and the task decision stays the same. That's not what this is. This is saying if the final residual is bumped by some value less than epsilon, then the task decision does not change. So it's still useful, but it's just a stepping stone to some stronger form of robustness. So that's the types of properties I prove. And let's try to just encode the transformer model as it is, and maybe we can just prove those properties. So we define what an input is. They're just bounded integers. Weights are floats. Embedding is just saying, so if the token at position T equals value I, then the embedding is just the corresponding row in the embedding matrix plus the positional encoding for position T. So this is definitely SMT expressible. This is very easy to do. You have residuals, which is just affine transformations. That's easy. The layer norm is the first part where it gets complicated. So the mean is linear because we know the number of elements, and summing elements together is tractable in SMT. The variance gets a little bit harder, and that's because this term, when you expand it, you end up with x sub I squared. So that's quadratic. And as a result, you can't use linear real arithmetic theory. You have to use nonlinear real arithmetic theory. And that's still decidable, but it's much less tractable. So that's the first issue. The way that you handle square root and the way that you express it in an SMT solver is you just square both sides and you have this auxiliary variable s. So this, again, we have a quadratic term or a quadratic constraint. You multiply both sides by the denominator. That's how you express this in SMT. And with this term, so beta sub I is fine because that's a constant. That's a affine transformation. You have gamma, also constant. The bad part here is y sub I times s. These are both unknowns. So now you have a quadratic bilinear form, and that forces you into NRA as well. So this is not the most efficient to compute in SMT theory. So as a result, we need some other alternative to this normalization operator. So now there's attention, and the way that attention works is you pass your values through this query matrix, you have it through a key matrix, Those are affine transformations, so those are fine. But then you do this dot product. And that dot product has all these bilinear forms. That's quadratic, so it throws you into NRA. So this is the first issue. The square root is over a constant, so this doesn't matter. And then we have a more serious issue. So softmax attention obviously has softmax. And softmax is not even representable in any decidable SMT theory. So softmax needs to be thrown out in some way, shape, or form. And then the way that softmax attention works is you have your attention scores, you put it through softmax, then you do a dot product on the values. That's a bilinear form again. So attention is really nasty. The activation is GALU for the default GPT-2 architecture, but I'm less concerned about that because there's a lot of alternatives. There's ReLU, leaky ReLU, so forth. So that's trivial to replace. So the bulk of this project is really, can we find an SMT-friendly normalization and attention operator? So this was the first attempt, and I basically said, let's not even prove the actual circuit. Instead, let's fit a surrogate function to the circuit. So I create some neural net, I make it so it's exactly equal to the circuit on the relevant inputs, and then I prove properties about that. And it's just a neural net with a linear unit ReLU activation. So I'll show you what this project's doing. And this is building on sparse circuits, one of OpenAI's projects, and they give a bunch of sample circuits that they extracted. One of them is called quotation matching. So if you have a single quote, then it should match that with another single quote. If it's a double quote, it'll match up with the double quote. So that's what quotation matching is. There's bracket matching, which is if it's a single bracket, it should match with single brackets. If it's double brackets, it should match up with a double bracket. So those are the two types of circuits. And what this is doing is it's asking whether those circuits are equivalent to a symbolic program. And the way that I represent symbolic programs is using this DSL. So this DSL is sufficient to represent the programs that we care about. And those programs are defined here. So this is a quotation program, and it's saying, gather all the different types of double quotes, given that there are different tokens that correspond to double quotes. Same for single quotes. And if it sees a double quote, then set this variable to 1, quote type. If it sees a single quote, then set it to 2. And when you're asked to output, then just check what quote type it was and output the corresponding value. So that's the quotation matching program. I have this helpful program that just renders it kind of like a Python program. So it'll take a DSL program and render it in a human readable form. This is the surrogate. So as I mentioned, it's linear, ReLU, linear, it's some number of layers. And this is training it to match the teacher function, which is a circuit. And the whole pipeline comes together here in this run equivalence demo file. So this will find the symbolic program that's equivalent. It fits a surrogate to the circuit, and then it formally proves equivalence or disproves it. And in some cases, it actually disproves it. So if you look at like the bracket program, it says that it's not equivalent, and it gives a concrete counterexample. So that's what that program is. And the weakness here is the surrogate, right? Because the surrogate is not the actual model. And we wanted to prove properties about the transformer model, not against this fake surrogate that may or may not be high fidelity. And this worked for small transformers, but if you had a really big circuit, then your surrogate fidelity might be an issue. So that's what motivates this project, where I want to just replace the activation, attention, and normalization operators with SMT-friendly alternatives. And these are like the first attempts that I had. So for the activation, use leaky ReLU, which I mentioned. Attention, use sparse max. If that doesn't work, then maybe do some kind of program search. For layer norm, we have this DYT norm. Maybe do a handcrafted alternative like a piecewise linear norm. And this is what the baseline results look like. So this is a GPT-2 model that I just trained locally. This is what the open web text loss looks like. This is the wiki text loss. So this is where we're starting at. And the question is, how close can we get to these values given all my alternative variants? So this is if you replace softmax attention with sparse max, and it's pretty close. So sparse max is decent on performance. DYT norm straight up did not work. I had some different piecewise linear variants, which I'll talk about. They diverged. And ultimately, I had to handcraft this band norm. It still was not great. Like, look at the wiki text loss. So I was actually training on OWT, and I was evaluating on wiki text. So this is the one that matters. And the perplexity is like way higher. And then this is the full stack where I replace the activation with leaky ReLU. And as you can see, the perplexity increase is pretty similar to the increase from band norm. So really the band norm is the issue. That's what's holding us back. And this is the way that I approach designing the band norm, where you just consider that layer norm is effectively projecting onto a sphere. It's projecting the activation onto a sphere. I had some PWL attempts so piecewise linear attempts, where sometimes I tried to do coordinate-wise clamping or coordinate-wise normalization. Ultimately, I did decide that global scaling is the correct approach. That's more similar to how layer norm works. But instead, the way it works is it's a more SMT-friendly approach. So the first step is you center it. So you subtract the appropriate value so that the L1 norm is equal to 0 globally. The second part is look at only the positive coordinates. And you sum up what that L1 norm is for only the positive coordinates. So that gives you some total mass. And then I make sure that that mass falls within some band. So that's the L1 band. And the way that I make sure that it falls within it is kind of similar to sparse max, where if it falls outside of the band, then I subtract the appropriate amount from every coordinate. Or if it falls below, then I add the appropriate amount to every coordinate. So that's the way that this band norm works. This is what the repo is. So most of the stuff here for this repo is under scripts. And the configs are where I actually define the different variants that I trained. So this is the final version where it uses the band norm and it uses sparse max. And as you can see, this is where it names the norm. And it trains it under this train.py file. So this is where it creates this object. This is where it defines the norm. And yeah, so this projection occurs after you've already done the mean centering. So I just call it the radius that we're trying to keep it within. And tau is the amount that you're subtracting from each value if needed. So it does the clamp, and if a value falls below 0 after subtracting tau, then we just clamp it at 0. So this is what the band norm implementation looks like. There's other useful stuff in this repo, like this is a small version of the transformer. So I wasn't able to use the verifier on extracted circuits for the GPT-2 size model, and I'll get into why. But as a result, I was only able to prove properties about a much smaller model. So this is a small model that I train, and then I verify those circuit properties that I referenced earlier. And this is just the verification pipeline. These are the SMT encodings. So like leaky ReLU is fairly straightforward, right? It's saying if x is greater than 0, then just set it to x. Otherwise, set it to some small rational number, alpha times x. This is the projection. So this one's interesting. So here we don't actually specify what tau is. Instead, we have this constraint where we just say, compute the projection, and then if the mass fell outside of the radius, then force the projected mass to equal the radius. And then it has to solve for the correct value of tau in order for this constraint to hold true. So that's the way that this is solved in practice. And like another note about some of those properties that we talked about earlier. So the way that you actually prove this in an SMT prover is you negate it, and then you ask it to solve for unsatisfiability. And in doing so, it'll produce a concrete counterexample if this property is not true. So just some details on the SMT solving for you. So this is the encodability, and this is the reason why it didn't work for the GPT-2 sized model, which is that the band norm actually works, right? By design, we made sure that it was just affine transformations, or it's doing fixed amounts that it's subtracting each value by. And I showed you what that encoding looks like. Sparse max attention still has bilinear forms. It's doing dot products between two different variables. And as a result, you're forced into NRA. So NRA theory is less efficient to compute. And as a result, we weren't able to actually prove properties over the large extracted circuits. The activation is easier. We looked at that encoding. So as a result, I do some proofs over a smaller transformer. And that's pretty much it for this project. So future directions, there's some actual work on removing the layer norm. So this is after training. At inference time, I guess they remove the layer norm. They do some post-training or some fine-tuning. and then you have a layer norm free transformer model. So maybe that's better for proving properties like this. That's probably worth exploring. The attention operator was a bottleneck, so it's worth trying to find an attention operator that's SMT friendly. And my prior on how we should approach that is you have some kind of decomposition, like the deep sets decomposition is one way that you can define a general class of attention operators, and then you search that class over SMT friendly primitives. So that's the way that I would find an appropriate attention operator. But even if we do those things, there's all these different problems that have to be solved for this research direction. So that's the reason why I put it on the back burner for now. But if you are interested in this, let me know. You can email me. This is my email. And let me know if there's any way that you'd like to collaborate.